Hi, good morning, my fellow learners. My name is Josiah Enrico S from Mechanical Engineering at FTUI, and today I'm going to show you my homework in Fluid Mechanics class number 3. So I'm going to show you my final paper or my final project of this subject. So let's get started. The title is Modelica-based simulation of viscous flow through pipes using finite element formulation. So what are we going to talk here? So we're going to talk about controlling and measuring several important properties in multiple pipe system. Though these properties are actually really critical, but unfortunately, the analytical way to calculate those numbers in several points selected is currently onerous and time consuming. So there is a need to find a numerical method or computer aided way to overcome these challenges. So one solution is using a programming language of Modelica. So this study will cover a Modelica programming language and compare it with the current analytical technique to verify the result. The simulation is expected to be a base in developing a scalable program for multiple pipe systems in further work. The background theory of this formulation is actually come from classical equation of Reynolds number. We are going to rearrange this equation with others conservation equation, let's say mass conservation and flow rate conservation, and we got a volumetric flow rate of related to head loss, which like this, and it's require the value of pressure at two different points, let's say P1 and P2. So we're going to keep this equation as the first equation for further work below. So let's move to the finite element formulation. So that equation will be separated, and then the prior part, this one will be substituted by a coefficient like this, and then we only have we only have three properties left. We're going to use these three properties and making a matrix equation like this. This is matrix which will be called flow resistant matrix, and this is consists of 2 times 2 elements. So this is the second equation we are going to keep. So this is the problem we are going to solve. As you can see, there are a multiple pipe system right here. It is consists of 6 different points and 6 different pipes connecting those points. And also, as you can see right here, there are also other properties like length and diameter in each pipe. Okay, we also got fluid properties like dynamic viscosity and density. And then after what, we have the boundary condition. We got the boundary condition at the first node, I mean inlet, and then the sixth node, I mean outlet. With this information, we are going to find out three results. The first one is the pressure distribution, and then the second one is the flow rate distribution, and the last one is the Reynolds number distribution. But also in this problem, we got other key point, which are the flow rate at the first node, it's equal to 5 times 10 to the power of negative 4 meter cubic per second. We're going to use this value for verification at the end of the result, at the end of the simulation. Let's move to the methodology. So there are two parts. The first one is analytical calculation, and then the second one is simulation program. So in the analytical one, we are going to use the second equation we keep from above. So this is the local elemental flow resistance of fluid flow. So we're going to use this equation to calculate the resistance at each pipe. So we're going to have R1 until R6. After we have all those numbers calculated, we're going to sum those up into one single global matrix, like this one. And then after we have made this global matrix, we are going to implement the boundaries condition. So we're going to make the first row and then the second row of the matrix to have identity element. We're going to solve this simultaneous algebra system with Gauss-Jordan or Gauss-Seidel, and we got the pressure as follows, like this. Using this information, we are going to get the flow rate, and then after the flow rate got, we're going to find out the Reynolds number, like this one. So let's move to the simulation program. The simulation program is divided into two parts. The first one is definition phase, and the second one is solution phase. So let's get started from the definition phase. As you can see, we're gonna rewrite all those information in the problem, start from the fluid properties in this part, and also we're going to put the boundary properties at the first at 6 node right here, and then we're going to put the number, the first one, number of pipe, and then the number of point connected. And then afterward, we're going to use the matrix of two columns matrix to define the length and diameter of each part. So let's say the first row represents first pipe, and then the second row represents second pipe, and so on. So, and also we got connection matrix also in two columns matrix. We got first row representing first pipe and second row representing second pipe, and so on. And also we already put the key inlet right here. This one will be used for the verification part at the end. So that's the definition phase. So the solution phase starts right here. It is using algorithm rather than equations. So I am going to use an iterating method at the first part, in this part, to do the local matrix and the global matrix calculation simultaneously. So as you can see right here, this is indexing the first local matrix for each pipe, and then this part is going to indexing for the global matrix, and this is the summation part where you are going to add all those local matrix into one single global matrix. So, and after we got the global matrix, we're going to implement the boundary. Then we're going to solve the pressure using information from P inlet and P outlet. And after we got the pressure, we're going to find the flow rate and then the Reynolds number simultaneously. That's how the program works. After that, we're going to get the results right here. So there are flow rate, Reynolds, and pressure results. If you compare these numbers to the analytical results, you can find out that all the numbers are quite similar because the deviation of those numbers is relatively small and only resulted from rounding. Thus, if the analytical results are correct, we could validate the simulation is accurate. That's the validation part. And then the verification part is we're going to recall one properties before. It is the flow rate at the first node. We already have 5 times 10 to the power of -4, but at the end of the simulation, we got actually almost the same number, just a very little difference of very little percentage of difference. So this number is quite similar, therefore it verified the simulation result. In conclusion, the Modelica-based simulation of multiple pipe system is feasible and it gives satisfactory result. This study also shows that using a computer-aided numerical method is more time efficient and recommended to solve complex engineering challenges. And the writer hope that the methodology used in this study can be adapted for further research in the future. I think that's all. That's all my white paper for my homework. So thank you so much for your attention. Thank you so much and bye-bye.